Imagine a bubble of air in a cup of water, and try and think of the answer. Your answer might look like one of these three. You can find this sort of answer on the internet, or by reading a textbook, or by asking a teacher or professor. They're all true statements, but none of them is the answer we're looking for, because none of them are an explanation of what's actually happening to the water and the bubble, and why it's actually happening. I had to come up with the answer I was looking for myself, so of course it might be completely wrong. Imagine a cup of water with a steel plate dropped on top which perfectly covers its surface. What would happen? Because you can't really compress water, the plate would just sit there on top and float. Now, if we imagine a circular hole is cut into the plate, and then we push down on the plate, intuitively, we know what will happen to the water. It'll shoot out of the hole. This fountain of water is what's actually pushing the bubble upwards, but to see why that's the case, we have to do a bit more imagining. Instead of a thin metal plate, let's imagine a fat sort of water donut. It's a cylinder of water which is the same size as the cup and fits in just like the plate did, and it has a section of water in the middle removed. We put the cylinder slash donut into the cup, and gravity pulls it down against the surface of the water. At this point, our donut slash cylinder will collapse if we don't plug the center, so we will. We'll fill the missing section with the cylinder of water. It's colored in differently to show where it is in the diagram. The difference is that at the bottom is a bubble of air which fits perfectly into this missing section. This section of water weighs less than a pure section of water because part of this section has been removed and replaced with air, namely the bubble, and air weighs less than water. So the donut is being pulled down onto the surface of the water. The cylinder in the middle is also being pulled down, but not as hard because it doesn't weigh as much. This is the same thing as our metal plate situation. Right underneath the bubble, there's less pressure, and so we get our fountain of water and it pushes the bubble upwards. This is sort of the intuitive picture of what's going on. What's actually happening is of course a lot more complicated than that, and you can go into more detail in a whole bunch of different directions. One thing that interested me is why a downward force would cause an upward fountain of water somewhere else. It seems like common sense that this should be the case, but if you imagine putting the steel plate slash water donut on top of, say, a block of ice, of course nothing shoots up. It must be something to do with the fact that this thing is a liquid. I think the answer is the way individual water molecules interact with each other when squeezed into each other. Imagine the metal plate being pushed downwards, and beneath the metal plate, 3 water molecules. Beneath the 3 water molecules, there's either going to be more water molecules, which act as a sort of floor as they're stacked, or the actual bottom of the cup itself. It doesn't matter which one. Of course, water molecules don't actually look like circles. It just makes the image clearer to use them. What matters is that the gap between each water molecule is 90 times smaller than the size of the molecule itself. So this image is roughly what's going on. If the 3 water molecules are lined up near perfectly, then when they're squeezed into each other, they'll just sit there like a stack of coins. This would almost never be the case though, because in water everything is always jiggling about randomly. If they're not lined up perfectly, then one of the molecules will shoot off in some direction while the other 2 come closer together. This is why the downward pushing of the plate or the water donut can make molecules move horizontally. If you get two of these horizontally moving molecules and they hit a third one, it'll go either up or down. In the case of the metal plate, it'll be empty space above and water below, so the molecules will be more inclined to shoot upwards. The case of the water donut is a bit more complicated. From below the bubble, you have this process shooting molecules upwards, and above the bubble, you have the same process shooting the molecules downwards. But the water donut that goes to the bottom of the bubble, and which is squeezing the water molecules that shoot upwards, is bigger than the one on top of the bubble, which is squeezing the water molecules that make them shoot downwards. And that means that the ones from below will hit harder than the ones from above, and the overall effect is that the bubble goes upward.